We'll have those up right. Okay. Okay, so first we got
Yo, I did looking at these, man.
an electron. So an electron's like a fundamental particle. It's really small and it's like treated like a point because it can't really be measured in terms of size because it doesn't bounce photons. It's the fundamental carrier of electricity for electricity and magnetism. Like almost everything revolves around the electron, so that's why it's important. It has a mass of 9.109 times 10 to the negative 31 kilograms.
Is that significant?
What?
Should we write that down?
If you
We
want.
can use it?
I mean,
Or is it,
sort
is
of.
it-
You
is
can
it
you can always look it up.
You
It's
said it's
just
a
a
point, right?
constant. What?
Or is it just a point?
Well, no, the mass does matter because it moves around. So it has like it like F equals ma applies to it when it has a certain amount of acceleration or a certain amount of force and has a certain amount of acceleration and velocity.
It'll be on the equation sheet.
Yeah, this is on the equation sheet. You don't need to write down, but it's just good to like see. Then it has a charge Q. Q is usually denoted as the charge of an object. Lowercase q is sometimes a point charge, and capital Q is more like a big amount of charge, but they're kind of interchangeable. It has a charge of 1.602 negative times 10 to the negative 19 coulombs. So coulombs is a unit of charge, or it's the SI unit of charge. But what's also sometimes called the charge of an electron is negative 1 e. So e represents an elementary charge. It's the smallest amount of charge that can possibly be transferred because it's the charge of one electron. It's not Euler's number, that's just a constant that equals this. Cool.
What's a coulomb?
A coulomb is a unit charge. Yeah,
Ooh,
there's not much more to it.
So it's like 1 coulomb.
Yeah, it's spelled
What is 1
I
coulomb?
don't even know.
It's like 1 kilogram Newton squared charge or something like that. It's somewhat big amount of charge.
Okay.
Yeah, it's a certain amount of ease.
How do they derive Coulomb again?
Yeah.
What do you mean?
Like, what is 1
What's
coulomb
equal to?
represent?
Just a certain amount of electrons. If you divide this on both sides, then you have like some big chunk of
What
10
is charge? Oh, ooh,
Yeah.
But like, okay, think about it.
Charge is like a fundamental it's a fundamental property just like mass.
Right.
You can't really break it down in terms. Yeah.
Charge is what?
Okay, that a 1 ampere current carries in 1 second.
Oh, okay.
That's not really helpful at all
What's
because that's sort of defined based on.
yeah, that's what I'm saying.
Yeah.
Yeah, charge.
Next we have a proton. A proton has a mass of 1.673 times 10 to the negative
I'm just writing
27
down what you said.
kilograms. So this is like 2,000 times bigger than an electron. And it has a charge of positive 1.602 times 10 to the negative 19 coulombs.
1.602 or 062?
1.602. It's the same as an electron except opposite. Which is interesting that they have, like, they're very different particles. Like a proton's much bigger. It's like in the nucleus of an atom. But it's the same, like, fundamental, like, something rather that makes up the charge. So that's equal to positive.
Who weighed it?
You don't need to weigh it. You can accelerate it with a certain amount of force.
Oh, so good. Okay.
So a proton has the opposite amount of charge as an electron, but it's much bigger, and that means that if we have like the same force applying on both of them, then the electrons could accelerate 2,000 times faster. And for that reason, also because like electrons are like outside of atoms and like protons are like part of the nucleus of atoms, electrons are the things that move around and carry current and electricity. Protons don't really do that. Electrons are things in motion through a wire. So like pretty much all of charge is based on electrons, which actually have a negative charge, which is kind of weird, but that's how it works. So yeah. Okay. Got my sock eraser here. They are.
I'm gonna eat that, man.
So here we got a plate.
No matter what.
A plate, this is just an example of a metal plate, and this plate holds a bunch of electrons.
Is it a plane?
Nah, it's a plate.
Okay.
Sorry. So this plate holds a bunch of electrons, and if the plate is conducting, then that means that the electrons can freely move around the plate. That's sort of what it means for it to be contained on the plate, like they're part of the plate. So if it's a conducting plate, a conducting material, the electrons can move around, and they'll typically distribute pretty evenly on the plate. But if it's an insulating plate, that means that the electrons are going to stay put wherever they are. So that they could be like more dense in some places and less dense in some
Bro,
places.
can you write some of this down?
If it's insulating.
Can you write some of that down?
You can write down whatever you want.
No, like say.
Okay.
You talk too fast.
Sorry. Insulating.
Like write down the important stuff that we should.
Yeah.
remember.
Don't move. Electrons. Conducting.
What's weird is like common knowledge though, like
Oh yeah.
conduction,
Okay.
like wires are conductive, so electrons.
Yeah,
can-
yeah,
it's
yeah.
like the current.
Yeah. Right. So that's why conducting stuff allows electricity to pass, and insulating doesn't. And that also leads to what happens if you have a 3D object. So this is a circle. I draw on the whiteboard like a circle, but you know it's a sphere. Woo, sphere. That helps. So this is a sphere. No, that does not help. And it can also have electrons in it, in its volume. However,
What is
if
this?
it's what?
What is it?
It's a sphere.
Just a sphere.
The electrons, however, will start to reside on the sides, typically, on the surface of the sphere. And that's because they repel away from each other. And they want to get as far from each other as possible. So if it's a conducting sphere, they reside on the edges. If it's insulating, they can stay in the middle.
Wait, so on like a conductive plate or whatever, they would go to the edges.
On a plate. That's a good
Oh no,
question.
they would go far, like as far apart from each other.
Yeah, they typically try to minimize the voltage. That's what it's called. I mean, you guys haven't learned the voltage yet, but the voltage is sort of like the potential. They want to get as far from each other as
Yeah,
possible.
so
to
I mean,
minimize the amount of
they would
forces.
space each other.
Yeah,
evenly.
they space each other evenly, pretty much. So that's a good question. Would they go onto the corners of the plate? I mean, okay. If you have enough electrons here, they'll start to like go in towards the center because eventually, like there's just too much for the density. So I think it's sort of the same thing with the plate, except with the plate it's a lot less common for them to be like only like a couple electrons. I'm sure at the first couple electrons there was
Yeah, if there were like 4, they would just be the
Yeah,
corners, right?
right, but they'll eventually start to distribute evenly. Okay. So then we have charge distributions. So we can also technically have a rod, and all of these objects are like 3D volumetric objects. But if we're treating this plate like it's really thin, negligibly thin, we call it like a surface. And if we treat a rod like it's really thin, we can just call it like a line. So let's say we have some electrons on this rod, electrons on this plate, electrons on this sphere. Let's assume they're insulating for a second. So it's an insulated rod. There's a certain distribution of the electrons, which is called the charge distribution. So if we want to describe that it's more dense at the beginning, for example, or more dense at the end, but let's make a real example. So let's say that as we get closer to the end of the rod, they get more and more dense. So first we have like a couple, and then they start increasing density. After that, I did that too fast. Now we have a lot of electrons at the end. So we can describe this charge distribution with the charge distribution formula. So the lambda represents a linear charge distribution, which is equal to dq dx, or L. Let's use x. It's like the amount of charge per unit of length of the rod.
What the fuck is that?
So we could say, for example,
Delta charge over delta.
that it was 1 coulomb
What is that?
per meter.
Oh, it's lambda. Lambda.
Yeah.
Half-life.
So So maybe it's 1 coulomb per meter is the density, and then we represent that the density gets more dense as we go on. So that's divided by or times x, x per meter. So this would be saying here that here's like maybe here's 1 meter, here's 2 meters, here's 3 meters, here's 4 meters. At 1 meter, we'd have 1 coulomb per meter times 1. At 2, we'd have 1 coulomb per meter times 2. So here we'd have like 1 coulomb per meter of density, here's 2 coulombs per meter of density, 3 coulombs per meter of density, 4 coulombs per meter of density. So they get more dense as it goes along using this formula. This is just an example of a particular charge distribution. And then we can do the same thing with the other ones.
Are charge distributions always coulomb over meter?
Or it would be negative 1 coulombs per meter.
What? Sorry.
Well,
Coulomb per meter. It's a meter because it's
Well, no, but like I mean for charge distributions in general, not just a linear distribution.
right. Exactly. A linear distribution is coulombs per meter.
Okay.
This would be coulombs per meter squared. This would be coulombs per meter cubed.
Oh, okay.
I was about to.
Wait, what is x in it?
X is just like distance. Nathan, what's your
it
question?
would be negative though, correct? Because they're.
Oh yeah, sure. Okay.
This professor sucks.
Sorry. So the symbol for a surface charge distribution, oh man, I forget to play the guitar, is a sigma, lowercase sigma. So this is equal to dq dA. And I'm sure you can imagine we could do some similar.
Is that a
formula.
derivative?
It is a derivative. Yeah. If we're deciding on like the charge distribution at a single point, you use the derivative. But if you're saying like this rod has a certain amount of charge, you could just use like Q over length for like the average charge distribution of the whole rod. So the derivative versus not derivative.
So you're taking the derivative of this?
Derivative of charge with respect to length. So as we're adding more length, we're adding more charge.
Sorry. You take the derivative with respect to x. Oh. You graph it out.
Yeah, the derivative is kind of misleading, I feel like. It's not really, I mean, it is a derivative, but it's not like.
But you could just say it's charge over.
So wait,
Yeah, but as you're, like, if you added more rod, for example, you'd be adding more charge.
You'd be adding less charge though, right? Because.
Well, no.
Oh, no, yeah, you're
Okay,
adding
so
more
at
charge
that
as
point,
well.
there's
less
4
charge. The
coulombs.
charge density would go down if you didn't increase
Yeah.
the charge though, right?
Yeah,
No,
but
I mean if you add more rod and you also add
Oh
more
yeah,
charge.
yeah.
That's sort of what the derivative represents.
Ooh, I'm gonna be fucking with these boundaries.
Like how quickly the charge is increasing at that point.
Dude, how much is that?
It's not the charge increasing at that point, it's the charge of the overall object.
So-
It'll be increasing.
So what? It's just showing what the charge is at that point.
Alright.
Okay.
The last charge distribution is volumetric, which is a rho. dq dv. These are the same symbols as mass distributions, which you might know from mechanics, but you just use them in context. So you got So the reason you might want to use one of these charge distributions is because a lot of the time when we get to Coulomb's law, we're going to be like integrating stuff to figure out a certain amount of force. And if you rearrange this, like if you have some integral dq, you can rearrange this equation here. So if we want to change it to like dx, if we move dx over here, then we have lambda dx equals dq. So this would just turn into lambda dx for like doing an integral over some like range or something. So yeah, we'll get to that in a little bit. But so here we have 3 examples. First we have 2 electrons. Second we have a proton and an electron. Third we have 2 protons. Or I guess these aren't necessarily protons. They could just be positively charged objects or negatively charged objects. Because usually we don't actually have protons going on. But we can see that if we have 2 electrons near each other, they'll repel. Here, a proton and electron will attract, and here 2 protons will repel. And that's because like charges repel and opposite charges attract. You probably already know that, but it's important, obviously. So yeah.
Oh, boy. All these.
Cool. So that leads us to the force that two charges exert on each other, which is the electric force, modeled by Coulomb's law. So if we have charge 1, Q1, we have charge 2, Q2, and they have some radius between them. Then the force that they exert each other, the absolute value of the force, is equal to K, Q1, Q2 over radius squared. This is all absolute value. Typically you're just going to decide yourself which way the force points based on like what you know about the system.
Wait, is that absolute value or magnitude?
There's also a formula that uses a vector, so you don't have to figure out the direction yourself. And if you want to use that, that's force vector of charge by charge 1 on 2 equals K times Q1, Q2 over radius from 1 to 2. Well, that doesn't actually matter. Radius squared times the unit vector from 1 to 2. So that means that here in this example, let's say they're both positive. The force by 1 exerted on 2, so this is the thing that's feeling the force, is equal to, or proportional to, both positive, so it's to be positive, over radius squared. And then this vector from 1 to 2, this unit vector would be 1, 0, because it's going from there to there. And it's a unit vector, so it has magnitude 1. So that would mean that the force would go that way. But then if we swap it around, by 2 on 1, 2 to 1, now the unit vector is going the opposite direction.
What's that? Oh, is that a unit vector half?
Yeah. So you can choose which of these, if you want to use the vector version or the absolute value version of Coulomb's law.
Is that
Yeah.
vector always negative
What?
1, 0?
No, it's just the direction, the unit vector of from 1 to 2. So if it was like charge here and charge here,
Yeah.
then the unit
Oh, it's
vector
just the
would be
direction.
this way.
Okay.
Yeah. From 1 to 2. Alright, cool. Okay. So also in
What is
Coulomb's
K?
law, K, exactly, yeah. K is a constant. K is Coulomb's law constant, and it's equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Oh no, units. That don't make any sense. Yeah.
Newton meter squared.
It doesn't matter. Just
Well,
don't worry about it.
we're multiplying the radius squared by the.
Right, you need to cancel everything out pretty much.
Cancel out and then.
Alright, the thing about this constant though is it also hides more information behind it. K is equal to 1 over 4 pi the permittivity of free space.
What?
The permittivity of free space is another constant. So the permittivity of free space sort of represents the relationship between the speed of light and the electric force attraction.
How do you spell that?
Permittivity.
Epsilon
Of free space. Yeah. Some people say permittivity in a vacuum. But also this value changes based on the material. So if you have some objects have like a relative permittivity of 5, meaning that their permittivity is 5 times higher, which would mean that all the electric attractions would be like 5 times lower, because this is divided in the formula. That make sense? No.
Wait, okay. The E thing, that's permittivity.
You don't need to worry
Epsilon.
about, it doesn't need to make perfect sense exactly what epsilon naught is.
Wait,
You
explain
can
what
use it for
permittivity of free space is.
It's like how much electric force there is for like a certain material.
how much electric force?
Yeah. Electric attraction. So like if you have these two charges in a certain material,
Yeah.
the different amount of permittivity in that material could change how much force they exert on each other.
Okay.
Sorry.
What?
No,
Does that not make sense?
I mean, that makes sense because it's like a truism, because it's like,
Right.
it's literally part of K.
Do you use it
Yeah.
in physics mechanics?
What?
Do
No.
you use for permittivity of free space in physics mechanics? Or sorry,
Yeah.
Oh.
So permittivity of free space, how the material changes, how much the force.
Yeah. Yeah.
Okay.
Okay.
What does that mean physically?
Well, material
It
is
doesn't really make sense physically.
Oh, so there's different.
I mean,
How
you mean
much?
like how does it affect it?
Yeah.
Well, you know how the speed of light can be affected by like
Oh.
Yeah.
So it's how the electrons.
sort of, not really.
Okay.
Yeah, it's weird.
How
But
much?
I think the speed of light does affect it, possibly, somehow. Speed of light sort of governs everything, including electric attractions. Okay, but the formula you need to know for permittivity of free space is the specific permittivity of something is equal to the permittivity of free space times the dielectric constant. The dielectric constant is the relative permittivity of a material.
Why is it another K?
It's
What?
it's not a K. It's the
What
Greek
the
symbol that looks like a K. I
Oh,
don't know how to. Yeah, kappa.
Kappa, oh my god.
Can you draw a better cap? So,
I don't even know how to draw kappa. It's like woo.
oh, that. Okay.
Yeah.
Wait. So okay, that's specific permittivity.
Right. So this is specific
For specific material. So
Yeah,
it's the
specific
oh, it's the permittivity of nothing.
vacuum, and this is relative.
Ah, I see.
What?
So if K is 2, that represents the material has twice the amount of permittivity than the permittivity of free space. Specific permittivity is just the value you'd actually use.
Okay.
This is like obvious.
We actually-
This equation's kind of saying nothing. Yes, you do use this
Okay.
with capacitors.
Oh, with capacitors, that makes sense.
So we got more values now. So I'm gonna draw a table of values.
Wait, the kappa is the dielectric constant.
Yeah.
Okay.
This is a table of 4 values. The first one we already know is force. And in this direction on the table, we're going to do a negative integral with respect to x. In this direction on the table, we're going to do a integral with respect to charge. So that means the opposite direction would be a derivative. So if we're going down this way, we're going to do negative d dx. And if we're going this way, that's negative d dq. And that makes sense. If any of the things you're doing is constant, you can always just multiply or divide by like q here if it's a constant q, constant x. The difference between an integral and like just multiplying you should already know. But yeah, so force is a vector. Its units are newtons. And then the equation we have for force is equal to k q1 q2 over r squared. I guess I'll keep in the vector thing here. 1, 2, force by 1 on 2. Alright. Does anyone remember what integral of force dx is equal to?
It's work.
Work or energy. So this is potential energy here. And the reason it's negative is because we're doing potential energy. Work is kinetic energy, so it's going to end up being negative for you to get that potential energy, which is kind of weird, but don't worry about it. I kind of think of this formula, if we're getting rid of like this unit vector and we're just doing this as a scalar, I sort of think of this as negative because you have to reverse the like forces. So that means over here, potential energy would be equal to positive k. Does anyone know how to integrate this with respect to x, or r is the same thing as x in this situation?
It would be negative, yeah, or K Q1 Q2 over R.
So this is the potential energy in between two charges. This is a scalar value because we did like a dot product integral sort of. X is a vector.
So you're saying if the middle is
Top product.
is negative K Q1 Q2 R squared, and then all of this.
The potential energy is K Q1 Q2 over R.
Oh wait, so okay, yeah, that's the magnitude, right?
Yeah.
Okay.
Wait, what?
Oh no.
Oh.
This makes sense?
Yeah, it makes sense. No, I mean like, Nathan, doesn't make sense.
Yeah, you guys are probably overthinking it. This is just integral with respect to X
Okay.
Of what?
of force.
Of the force vector.
What is N?
N is newtons. This is
It's
just
like
represent the units.
It's like the type of the
Yeah, I'm not multiplying it. The brackets
Force
mean
by
this is
particle
newtons.
1 onto.
Yeah,
The
Okay.
potential
I forget
energy is in what's that in?
joules.
So what is in the
Joules or
bottom?
Newton meters. And that makes sense because we multiply meters when we did the integral with respect to X.
What's in the bottom right?
Bottom right.
Yeah. What is that? Is that supposed to be in there, in that bottom, in the
What are you talking about?
negative K Q1 Q2?
This is the formula for force. Jacob's a little confused. Okay, Jacob.
Okay, so you're saying that. Why don't you put it up there then?
Because I want to show that, like, there's more details I'm going to put on each of these things. So with force, what if we had some Q here that was in some charge distribution? If we want to change this into an integral, how could we change this formula to be an integral formula? I don't know.
Q squared.
We could like change Q to be dq and put an integral over the whole thing. So integral K dq Q2 over R squared. So yeah, you can choose to use dq or just normal Q in any situation. And the same thing here. You might need to do integral K dq Q2 over R, or like these 1s, 2s don't really matter. Like you can change that to a capital Q. Okay, next value. But first of all, just remember that integral of force with respect to integral of force dot ds equals negative potential energy, and then negative du ds or x, doesn't matter, is equal to force. This is what this up and down represents, these formulas here. Okay, so if we go to the left side, does anyone know what value is over here when we take the derivative with respect to Q of force? D force dq. This is electric field vector. Electric field vector is measured in newtons per coulomb, because we just divided coulombs out here. An electric field is sort of a weird concept. It's the amount of force that something would be exerted by something else per amount of charge that thing is. That was a terrible explanation, but
What?
let's say we have some group of charges here, and we had some like negative, here we had like 1 electron, here we have a little cluster of 2 electrons. If we were figuring out the force in between these two objects, here we'd have some force, and here it'd be twice the force, because there's twice the amount of charge here.
Yeah.
However, these things are in the same amount of electric field, because they have the same amount of force per charge. So that's sort of just based on distance and this amount of charge in the center here. So electric field lines, you don't need other particles. You only need one particle here. And then you can say like, oh, here there's a certain amount of electric field, here there's a certain amount of electric field.
So it's just a measurement of electrical field?
Yeah.
Okay.
That's exactly what it's called. Yeah. And it's a vector, it's like force, but it's not exactly force.
Well, it's proportion of the force.
Because there's a
Yeah.
different amount of force where you are.
It's like the amount of force based on how much charge.
Distance?
And charge and distance.
Oh,
that
yeah.
way.
Yeah.
It's like if there's a particle with a charge, the electrical field at a point around the charge will be equal to, I think Coulomb's constant, right? Something. How's it measure field?
Anyway, well, we can find out the formula right now.
Yeah, okay.
So what's the derivative of this thing with respect to Q?
Just Q2 over R squared.
Which Q?
Sure, it doesn't matter. Negative KQ over R squared is electric field. And then you can do the same goofy thing where you put some back in. Yeah, so that's the electric field formula. And then we have one last value. Can anyone guess? Or sorry, I guess first of all, so obviously here we're taking the derivative with respect to Q, here we're taking the integral with respect to Q. Integral is like the same as multiplication. Derivative is the same as division. If we have a constant, like little amount of charge, then we just say that F equals QE. This is sort of an important formula. So the amount of charge times the amount of electric field is how much force it is going to experience. Yeah.
I thought electric field accounts for the.
Electric field is what determines the force.
No, charge.
Charge, well, this is the
Electric
charge
field
of the
have-
thing experiencing it. There's the charge of the thing creating the electric field and the charge of the thing experiencing the electric field. So it's the charge of the thing experiencing the electric field.
Oh yeah, that makes sense.
Thing experience. So we use it. Okay, so Q is total charge.
Q is the charge of the experiencer of the electric field.
Okay.
E is the electric field it is in, and force is the force that it experiences.
Okay.
Some little particle here. So there's a certain amount of electric field and a certain amount of force.
Oh, I think I might know what the last one is.
Guess?
Electrical field potential.
Which is also called what?
Voltage.
Voltage.
Oh.
Volts is measured in joules per coulomb. So the amount of energy per amount of charge. This is like electric field. So like this is the reason I drew this square is because it's like a good analogy. Potential energy is the force, like voltage. I need to stop doing that. Voltage is to electric field. And these four you can all like go from each other. Also, electric field is sometimes called volts per meter because you take volts and divide by meters, which is really stupid. Because volts is really just joules per coulomb. Joules is really just Newton meters per coulomb. Newton meters, when you have the newtons cancel, it's like the same thing, but it doesn't matter. So this is an alternate unit for that. So volts. Does anyone know the integral of negative Q KQ over R squared?
With respect to
It'd be
X.
KQ over R.
Yeah, KQ over R is equal to voltage. So yeah, we have F equals QE, and then that means that U equals QV. The amount of charge per voltage is the amount of potential energy it experiences. Jacob, is this all making sense?
What's the difference between the big one and the little one?
The big what?
Q.
It does not matter.
Yeah, it's the
You're
same
thinking
thing.
about the wrong things here.
Okay.
Q specifically at a point, but then big Q, the small Q's are specifically at a point, I think, but then big Q can.
They're all interchangeable. You can swap them in
Yeah.
using whatever form.
Usually they use
What-
big Q
what-
for like.
what is this?
and,
Right here, huh?
What?
In the bottom, or
Force?
right here. What are you doing?
This is if I want to do an integral instead of
Like, why'd you make it a big Q?
because like this is some big chunk of charge. Like let's say we have a rod. We're gonna get to this problem in a second here. We have a rod and then a little charge attracting it. This like has some big charge and this has some little charge.
Okay.
And this is
pretty
at
much a small Q is just at a point, usually,
Yeah, and the Q is at like a whole object.
like an area.
So we're gonna have to integrate this because this has
So
Like
we're
a charge
thinking of
distribution.
force as a function of Q.
yeah, sort of, yeah. Okay, so actually we're about to do a problem like that. But first we're going to visualize these constants with a little picture. So let's say we have some charge, we're just gonna call it a negative charge. I'll also do the same thing for a positive charge in a minute here. We can represent the electric field of this charge. We can draw it with arrows. If we draw an arrow, this is the electric field line of
And then
this.
usually the arrow is going positive, right? So the field is going towards the electron, but away from the positron.
Right, sure. That's because the arrows represent the direction that a
Of the
positive
the
positive test charge would move. So if we had a little a positive test charge is a theoretical like little charge that has positive 1e charge, doesn't have a mass, doesn't affect the system. It's just a test like the electric field. It's a stupid idea, but yeah. So the arrows point towards the little electron because the electric field is going that way. And the increased density of the arrows represents the increase in electric field. So more sparser arrows is less electric field. Here because
I thought longer electrical arrows were more field.
See how there's a lot more arrow density here and a lot less arrow density here? That represents how there's less electric field over here than over here. Makes sense? Less magnitude of.
Like, would it be like this? Or would it be
I mean like the total amount of, not the length of the arrows. So like how much line there is.
Oh yeah, okay.
So
But would it look like
what is
this?
the length?
Or
Okay, what is the
this?
length of the arrows showing?
The length of the arrows is not relevant.
Why you draw them longer then?
What?
Why'd you draw that?
Why didn't I draw them longer? Because I was lazy.
No, why did you draw those longer? And those up there shorter.
That was not intentional.
Okay.
Yeah.
That's it.
So higher charge.
I guess I should have drawn these.
So it demonstrates the. Oh, okay. It demonstrates
So
how
what-
strong the electric field is by density.
Yeah, right.
Yeah,
Yeah,
the
that's-
density of the arrows. Okay.
Okay.
Strength.
And then which way will the arrows be pointing for the positive one? The positive one, the arrows will point away from it. And this little pair of a negative and a positive opposing charges is called an electric dipole. And we can draw, if we sum up these arrows, we can draw a more complex electric field. So if there is a little positive test charge,
What's a dipole?
a dipole is a pair of a negative and a positive charge. Yeah, I don't know why, but it's just like an important concept to know. But anyway, the electric field of this whole thing, if we add up all these arrows, so remember these are going like longer, so like this one will be over here, this one will be over here. The addition of this way and that way are going to add up to an arrow that way. Because the electric fields are like superimposing each other. So this total electric field is like this.
Whoa. No. That's the magnet thing, right?
Yeah, it's exactly it's how a magnet looks like, sort of. There's also magnetic dipoles. And then this will go infinitely long because it never really connects, which is kind of stupid. This is what an electric dipole looks like.
What should I call this? Electric dipole?
Yeah. Playing Take Me Out by Friends from.
My dad was like the CD or something.
Really?
The album, there's one song anyone else listens to. Do they
Okay.
have any other songs?
Yeah, I think there's another one that I might listen to. Maybe.
That's right.
I think there was. Okay. Anyway, so we have electric field lines, and then we also have a concept of isolines. Seve and Jacob, you both know about isolines. We learned about in Calc 3.
Iceland?
Isoline.
Isometric?
An isoline is equal electric field and potential. So we can draw a line here. And
Oh,
a line
yeah.
Here,
Oh.
a line here.
Oh,
Along
right.
this line are all equal
So it's like a
Oh,
electric fields.
yeah.
And then
it's
they'll
like a
start becoming
topographic
more
map
eccentric.
of
Yeah.
the charge.
Using your AFO
Yeah.
knowledge.
Exactly. Yeah. So on these lines we can mark a certain electric field and voltage value.
Is it one would be positive, one would be negative? In
Yeah.
those lines?
Okay, wait, so first I'm gonna do voltage, because voltage is more commonly the thing drawn on isolines. So voltage is considered 0 when it's infinitely far away from any charge. So over here is 0 volts, over here is 0 volts, or close to 0 volts. And as we get close to a charge, that's when the voltage is going to either increase or decrease, but it's going to increase in magnitude. So close to a negative charge, we're going to have a very negative voltage. Here we have maybe 20 volts. And if we get really close, we can eventually get to negative 50 volts because you can't crush stuff all the way right next to a charge. Here's negative 10 volts, here might be negative 5 volts, maybe we have negative 2 volts, negative 1 volt. And then close to the positive one, we have opposite 20 volts, 10 volts, 5 volts, 2 volts. These isolines represent a constant voltage. And something interesting is, so you guys know that potential energy will always try to be decreased in a system. That's like the definition of like how energy works. And voltage is also trying to be decreased in a system. So if we have like a positive test charge, the positive test charge is decreasing voltage as it travels along the arrow. So in the direction of the arrows, we always have a decrease in voltage. So over here you see that it's decreasing towards negative infinity, as it points towards it. And over here, it's pointing away from it. So it's increasing as we go upstream of the arrow. Cool. Okay, you guys have this all down? Okay. Just so you know, this is also, if we have two positives or two negatives, then the electric field lines are going to look slightly different. They're going to look like this. Whoa.
What do the ISO lines look on that?
ISO lines are always perpendicular to electric field lines, by the way. You can kind of just I guess there's going to be an ISO line like way up here. So there's a whole ISO line outside. Yeah, I don't really have a sketch of the ISO lines, so I'm just going to eyeball it. Something like this. Oh, right, it starts to go like this. That's a nice one.
Tits.
Great, yeah.
Why?
What?
That's supposed to be separate.
Wait, what?
What?
It's the same potential across the entire ISO line.
Yeah, that'll be separate.
Voltage.
The reason that the ice lines were never connected over here is because one was negative and one was positive, so they're like different.
Isoline is when the potential energy equals the voltage.
No, it's when over the entire ice line you have the same amount of electric potential or electric field.
Oh, I see.
We're going to do an example problem. So let's say we have a rod. And we have a little charge. We're going to try to solve for an expression of the force vector that the charge experiences. So let's say this rod has some charge distribution. Lambda equals 3x squared. This I guess would be in coulombs per meter to the power of 4. Sorry, to the power of 3. If we want coulombs per meter, we have 2x.
Oh, it's not a line. It's actual rod.
Right.
Okay.
Well, we're treating it linear.
Then wouldn't the charge density be
It's not meter
c
cubed.
squared?
The whole units of this thing is going to be coulombs per meter because we have x multiplying
Oh.
x squared. Yeah. Okay. Can anyone start me on how to solve for the force of the charge?
You find the electrical potential field or something?
We do not need that.
You find that, sorry, electrical
Wait,
field.
find what?
So we have Coulomb's law.
Okay.
Force vector equals
What do you want us to find?
the force vector of this.
Oh.
Yeah, you find the electrical field at that point, right?
What?
You
You
find
don't
the
need
electrical
you don't need to use the electric field. You can just use the force directly. But yeah. Okay. So we have K integral of K Q1 dq over r squared. And then we also need to actually use a real unit vector.
Times 1e.
Force.
Shucks. Is it k times lambda times x times 1e? Oh, it's not.
Okay. So the first step, I need a spicy mango. Sorry. I'm going to do this.
Why do we have to integrate? Oh, because it's a. Oh. Wait.
First of all, how do we change dq to be more useful? So, how can we rearrange dq to become to a dx? We know that dq dx equals this whole thing.
I
How
don't
do
know.
we rearrange this?
Really?
dx over lambda? No.
It's
Lambda over lambda
times
dx.
dx.
Lambda,
Yeah, lambda times dx.
I was close.
And lambda is equal to this, right? So dq equals 3x squared coulombs per meter cubed dx. Right?
Yep.
I feel like those units are wrong. No, those units are right. Okay. So that means that this is. I don't like that. They're gonna become closer. Sorry, I never assigned. Recall this meters equals 0. Here's meters equals 4, and here this is at point 3,4. This has a charge of 2 coulombs. We already have the charge distribution on the rod.
Is that 4-3 or 3-0? Or 4-3 or 3-4?
And you know, recently I've been putting all my coordinates backwards. I have no idea why. 4 meters, 3 meters.
Oh, caught the teacher lacking.
Yeah. I mean, we could do either way.
And then at
Is
the
that
very
true?
left of the rod is 0-0?
Yeah.
Okay.
So this is going to be equal to k integral q1 3x squared. I think we can drop the units for now. You shouldn't do that, but a 3x squared over r squared r hat. Now put dx at the end.
This would have been nicer if we didn't do the direction too.
Yeah, unfortunately we have to do the direction too.
What's the charge of Q1?
Sorry,
Two-
right. 2 coulombs.
2c.
So we're just gonna put 6 x squared over r squared. We're getting rid of units because we know that the units are just gonna be newtons. Although you should probably write the units in on the FRQs in the AP test.
No.
Okay. So what do we do with the bounds of the interval? Typically, you want to add the bounds of an interval as soon as possible when you're doing it. What are the bounds of this interval?
What are your cube like?
0 to 4?
Yeah, 0 to 4, because we're integrating over this.
Oh.
4 meters, we're gonna drop the unit because we don't care. Okay, now what is the expression for radius?
What, it's from the center?
So it's from here to some point.
Wouldn't it be from the... Aren't you integrating from the center of the rod though? Because that's the... Or no. Are you doing it from the center of the charge distribution or what?
What?
Where do you like? How do you find radius? Where's like the radius from?
This is the thing experienced in the force, right? So
Yeah.
the radius is how far from each individual point that we're in.
Oh, that's why we're doing an integral.
No way!
It's the integral is the charge. It's
Wait,
the integral of the
What is the integral? What is the integral?
It's the integral of all the forces exerted on the point charge by and your
You know, a
Yo!
cool thing to think about is it's like
think
df. df is equal to k dq q over r squared. Right, and then we're integrating both sides
No,
to
you just
get
confused me, man.
f.
Shut up, Miles.
No? I'm just teaching. You see this df? That help or no?
What is that? What?
Okay, so you know the formula for integral k dq q over r squared equals force.
Oh,
Wait,
okay,
so is
okay.
R equal to
Wait, okay, so you're saying
So df
force is equal to
R is
k
based off
dq
X.
q over r squared, or no, k q1 q2 over r squared,
Yeah,
and then
we're integrating stuff.
okay.
wait? So is R equal to the square root of 4 minus x squared plus 9?
Yeah.
Is the square root of that?
Yeah.
Okay.
So we have to determine the height. So the height is
Light work.
the height is 3 meters, and here this is gonna be 4 minus x.
Oh.
So radius, this whole integral now we're gonna have
Oh.
k integral 0 to 4,
That Pythagorean
6x squared over square root
Yeah, but then
9 plus squared, so it's gonna cancel out.
Not
9 plus 4 minus x squared. And we still have r hat.
I mean, I plug that into the calculator and it does it for me, right?
Right, you don't need to integrate this.
Yes,
We're looking
yes.
for an integral expression. We're almost done.
Please don't erase this. Oh, I gotta write this all down.
What?
dx?
dx.
Yeah. Oh, fucking.
This is like lacking number 3, yeah.
Also, it's supposed to be the square root of 9 plus 4
No.
minus x squared.
Squared.
Positive always.
Yeah.
Distance can't be negative.
Although, actually, I think I do want to leave it as a square root squared. Because I'll show you in a second.
Oh no! Mmm.
Man.
I just realized.
You realized why?
No, I lied boldly and brazenly in your face.
We need to solve for r hat. That one's a little bit harder.
Shoot.
How do we do r hat?
R hat's equal to.
It's just the.
It's just the distance.
So the distance at the top and then the magnitude at the bottom.
Yeah.
Square root of 9 plus 4 minus x squared again. Does anyone see now why we didn't square out the square
So
root?
it's cubed.
Right, it's the square root cubed, just like we had.
Oh.
That's 4 minus x, comma 3.
4 minus x, comma 3. Good job.
Oh.
So our final formula here. Okay. If we want to separate, do we want to separate out this force vector? No, let's just leave it in one. F. Here, I'm gonna do it in a different color just because we found a solution and we're so happy. F vector is equal to k integral from 0 to 4 of 6x squared over square root 9 plus 4 minus x squared
Cube that.
times 4 minus x, comma 3. And that is our force expression.
No, what happens? I get it.
Dx?
Oh.
Oh, no, not this time, not this time.
Tisk tisk.
So if you wanted to find the force x component, by the way, then you just use this. You multiply just this. And you want the y component, you multiply just this. Or you could also change this whole thing. You could distribute it out. So you can be like force equals vector, and then be like k integral yada yada.
Do you have to
K
simplify
integral
this?
yada
Do you have
yada.
to simplify this?
This is simplified enough for an integral expression, I think, for like 80 questions.
Okay.
Oh, that's
It's
it?
easy, it's easy.
What was that easy?
Light work.
Light work, no reaction, right,
Yeah,
guys?
so-
Light work, no reaction.
Well, okay, so you
Oh,
can
yeah,
write.
it's
You can just write that.
complicated.
This is probably good enough. This is like a question. This is an overcomplicated question. I think they'll give you easier ones.
Yeah.
Whew.
But
So
yeah.
we're gonna.
This is the hardest it gets.
Oh, no, not the hardest.
No, electrostatics is actually free compared to some of the other magnetic stuff, but yeah, we'll get there. Okay.
Is that it?
No, we have another problem. And it's completely different. Sorry. Alright, I would like to do some justice to this problem of calculating the charge that would be distributed in between two spheres, because I kind of messed it up in my first lecture. So anyway, we have two spheres. One's here, one's here. And let's say that this one has an initial charge of 2 coulombs and this one has an initial charge of 1 coulomb. Maybe this one has a radius of 3 meters and this one has a radius of 1 meter. And we're trying to determine if we connect a wire between them, both those spheres are conductive by the way, where the charge will move in between the spheres. So yeah, okay. First of all, we need to figure out the method that we're going to use to solve this problem, and that method is setting the voltages of the two spheres equal to each other, because whenever there is a connection between conducting objects, they will try to equalize the voltage to be the same in between them. So the thing about spheres is if we inspect the charge distribution, it's going to be along the surface of the sphere. This is just a 2D cross section. It's actually going to be 3D, and then have a 2D surface of charges, not just a 1D one as shown on the whiteboard. But the thing about these charges is, if for example here we look at this little charge here, this is pushing on all of these charges in the sphere. So each little dq has another dq to worry about for the amount of voltage in between them. However, a very convenient property about spheres like this is it actually turns out that all of these charges in this spherical distribution around one of this other charge will act like they're just all concentrated in the center as a point charge. And this one is having an interaction with it that way. So all these charges add up together to make a force just like that on this little charge here, which makes it actually a lot easier to calculate the voltage of the sphere. So this is a property you should remember. Anyway, so if we treat all the charges as if they're in the center here, we can call the entire charge of the sphere Q, and then we call this little charge here dq. And we know then that dV, this little voltage from dq, is equal to K dq over R, because of our voltage equation. And if we integrate both sides of this, so this is over the entire surface of the sphere, we're going to get V is equal to KQ over R, which is interesting because this is exactly the same formula as if we just had 2 point charges and they were exerting a force on each other and they had a voltage. So you can now remember for the future that a sphere has a voltage of KQ over R when it's conductive and it's distributing charges throughout it. And that's a convenient formula for the next step in our derivation. This is a little bit of circular logic here, especially because I made the simplification of all these charges acting like a point in the center, but it is correct. So there's the thing we're going to use. Cool. So anyway, the next step is we make formulas for each of the voltages here. So we have V1 of sphere number 1 is equal to KQ over R, and we're going to do Q1 and R1. And here we have V2 is equal to KQ2 over R2. So then when we set them equal to each other, we have KQ1 over R1 equals KQ2 over R2. The K's cancel because they're on both sides. And then to get the ratio of the final charges that we're going to have on both of the spheres, we have we're gonna swap these by cross multiplying, which is actually just dividing this and multiplying this. So we have Q1 over Q2 equals R1 over R2. So that means the ratio of the final charges is going to be equal to the ratio of the radius, of the radii of the two spheres. And we also know that Q1 plus Q2, the total amount of charge is going to remain constant in this entire process. So this means that, let's plug in our values now. So the final Q1 charge over the final Q2 charge is going to be equal to radius 1 over radius 2. So 3 meters over 1 meter, which is just equal to 3. Q1F over Q2F equals 3. And then we know that Q1F plus Q2F is also equal to 3. 3 coulombs, actually, because we add up these together. So Q1F plus Q2F equals 3 coulombs. And then the easiest way now to solve for QF is we will substitute in this equation a conversion to substitute for our system of equations. So if we move this over here, we have Q1F is equal to 3 times Q2F. So that means we can substitute 3 times Q2F in for Q1F. 3 Q2F equals, plus Q2F equals 3 coulombs. So we know that 4 Q2F equals 3 coulombs, and therefore Q2F equals 3 over 4 coulombs. So that is the final charge after the wire is connected for the second one. So this is going to be 3/4 of a coulomb. And we could do the same substitution to solve for the first one, but it's easier to just use the first formula. So we know that 3/4 of a coulomb plus Q and F is going to be equal to 3 coulombs, and therefore, if you do the fractions, you get 9/4 of a coulomb is going to be the final charge for the sphere. So that is how we would solve that problem.